believe the term is in order. Hello world, right?
All right. Okay, so
I
we
wanted, okay, good. Guys, before we go over the latest material, I thought it'd behoove us to go over linear dependence and independence very briefly. Again, I hope you're watching Saul's lectures, and I hope you're even watching them multiple times. And if it's starting to become familiar, don't even hesitate to put it on 2x speed. But, watch it, work through our examples, think about it. And then it's very valuable to watch it again, work through our examples again, and think about it. And even if you're inclined, try to code some of this stuff from scratch. But briefly, let's recover what it means for vectors to be either linearly dependent or independent. And again, I try to put all the links to Saul's lectures here that we're using Python and LaTeX to help us understand better. So linear independence, again, and I'm mixing our language with linear algebra and data science, means there's no collinearity between two vectors, two or more vectors. In fact, let me change that. Usually we're just thinking about two vectors, but or features. But when we say there's linear dependence, that means there is collinearity present between two or more vectors. And there's a way to describe the vectors from two other vectors, and that will become more clear. But these are stupid simple examples of dependent vectors. I've got 2 here and 1. And we saw that, well, wait a minute, all I have to do is multiply vector 2 by 2, and now they're exactly equal. Or I could have, in the same way, divided vector 1 by 2 and had 1, 1, and 1, 1. So anytime I can just scale one vector and make it equal to the other one, there's dependence between those two vectors. And this is usually easy to see by inspection, but what if we've got a ton of dimensions? We need a mathematical way, that is a code way, a programmatic way to check for dependence or independence. And this is why I introduced you to creating unit vectors, because that's going to be really important also. Oh, just a fun thing. You hover over this and it'll give you some helps about the linalg module from NumPy. That's true of anything you hover over. So that's a nice thing when you're in Google Colab. But how did we do that? We took the norm, that's the Euclidean norm, or if you're looking at a triangle and you're looking at the 2 legs of a right triangle, that would be the hypotenuse. So we're just talking about the norm, but you can get the norm in more dimensions than 2, or we wouldn't necessarily call it the hypotenuse then, but I hope you follow my meaning. So we're dividing these by the magnitude of the vector to get a unit vector, so that this is pointing in one direction and this is pointing in an independent direction. And when we get the unit vectors of these 2 original vectors, we see they're exactly equal. So what we're talking about is dependence is present when you can scale the vectors you're looking at and make them equal. And that's what we mean by dependence. But independence is when there's no scaling of the vectors that you can do to make them equal. So here we've done the unit vector approach on, we have 2, 2, and 1, 2. And when we do that unit vector approach, we find that, oh, clearly there is no scaling of one of these vectors that will make it equal to the other vectors. So those are independent. But a general check, just mathematically speaking, for independence, let's say we have these 2 vectors again. if there is a C1 not equal to 0 and or some C2 not equal 0, to satisfy the equation some C1 plus some C times V1 plus some C2 times V2. And by the way, we should say something about these, each of these. So we agreed not to put ourselves through the pain of coding in LaTeX real time during these videos, because the last time we tried that, it was a fiasco. Thom found he couldn't think and code in LaTeX and lecture at the same time. So what we really want to say is for all real numbers. So I'll just say that in text here, but improve it later. For all real numbers. And I should really say for C, we'll do at least a little bit of LaTeX. It's simple. By the way, you can get very fast at coding in LaTeX, but trying to code for me, trying to code and talk about it for C1 being any real number. You can get to where it's not hard to code in it, but I would encourage you to keep that some type of LaTeX math cheat sheet open. I'll go show you mine again. Here we go, blog. Well, yes, thank you for that. Okay, here we go, blog, LaTeX. And this is the one that I like to use right here, and you'll see it's, I'll put this in the chat again. Oh, and thanks for sharing the notebook there in the notes. Here you go. But this is where I grab it from. And so what we're just trying to say for C1 being any real number, and then let's do the same for that C2, because that's what we're really trying to say. And I'll improve this. I'll make it more mathematical looking using LaTeX later. But, and so what we're getting at is once that's, if we can find some C1 times V1 and some other C2 times real V2, where C1 and C2 are from the real number space, to make this equation equal to 0, then the vectors are clearly dependent. That's what we were really saying above. But if C1 and C2 must be 0 to satisfy the equation above, then the vectors are independent. So we went through some visualizations of that. If we see the two vectors lying one on top of the other, then we know they're dependent. And really, what that's saying is, even though we have two vectors, one of those two vectors is not giving us more information. Whereas when we have independence, they are giving us more information. They're widening the space, so to speak. And so with increased dimensionality comes new information. It almost sounds like something Uncle Ben would tell Spider-Man, doesn't it? Now, what I'm doing when I do decide to do a LinkedIn post, I'll try to call it compact review of, and then I usually just copy and paste or screenshot the stuff below compact review, but maybe I'll change it to say LinkedIn post. You know that these classes are sometimes going to LinkedIn post. And so we created this little test here too, with what we've already learned code-wise, to say, if I've got these two vectors from above, with all that we went through, now we have a programmatic way to rapidly check if they're independent or dependent. And so if independence is false, it's dependent. And if independence is true, they truly are independent. And so we see it both mathematically through these steps and visually. And we went through this in another recording. I'm just going through a brief review now. Now, this is where we were last time. And let me scroll up our, and
Sorry, Dad, before you go too far, please could you scroll down a bit to the chart, Matplotlib?
up here, you mean?
Yes, absolutely. It's great, great.
Now, what's the question?
Okay, so now looking at these vectors, they have different magnitudes. That's the dependent vectors. They have different magnitudes. So since one has more magnitude than the other, would it be right to say, okay, we can actually safely knock off the other one that has the smaller magnitude, since it is not giving us too much information as this one that has a higher magnitude? Would that be like what happens in PCA, where we transform a vector space, knocking off the vectors that are not giving us more information because of they're all collinear? Would that be what's happening?
Sort of. And I'm glad you're asking that. It's sort of like that. When, let's say you go that it's the way we're looking at it. Let's say that this is a 2D projection right here of a larger dimensional space. And so in a way, what PCA does for you is it rotates this view enough so that all the vectors are independent. Now, it's hard to see what I'm saying right now. We are definitely going to understand PCA inside and out as we get deeper into these linear algebra lectures. And what we're doing right now is laying a foundation of understanding of spans and subspaces and spans of vectors, spatial spans defined by vectors. We're looking at sets of vectors. We're looking at what it means for a set of vectors to be a valid subspace. And then we're even today looking at what does it mean for a subspace of vectors, a set of vectors that defines a subspace to be a basis. And so remember my stones just under the water level of a river, the PCA stones are a little further across the river, and but they're important. We just aren't quite there yet. But it's a way to, when we get into transformations in linear algebra, you'll see that, oh, okay, when we use PCA, we're transforming the vectors that are in our set of vectors that define a subspace, and we're actually transforming them into another orientation so that they're all independent. But we're not quite there to understand how to do that yet, but we're getting there. Okay? You're on mute. Is that good, Hugo?
Yeah, absolutely. My bad.
Okay. And if it's not, we can talk about that a little further, but we will get to PCA. Now, but the way I want you to see this now is, well, if these are laying right on top of each other, clearly I could multiply this one by some value C in the real number set, or I could, to make it equal to this one, or I could multiply this one by some real value C in the real number set to make it equal this one. Or, like we've been doing, I can divide them both by their magnitudes to get a unit vector and make them equal. And that's kind of what we've been doing programmatically. So, because I wanted y'all to also see the power of using these norms from the linear algebra module. Okay. So now we're thinking about subspaces. If we have a set of vectors, how do we find out if they defined a valid subspace? And how do we find out if that set of vectors is what we call a basis, or really a foundation to describe a subspace? And we're going to learn what those mean. Hang on a minute. So in linear algebra and the data sciences, um, they're both subsets of STEM. And I know we went over this last time, but I think it's worth repeating. Sometimes it takes learning several lectures or sessions or chapters of STEM material before the lights turn on in your mind. So it's kind of like you're reading a novel right now, and you're really eager to find out what's going to happen later. And the material can be kind of confusing, even when you're reading a great novel. But after you've read the whole thing, if you read that novel again, you pick up more details the second time through. And that's very much similar to the way our learning sometimes needs to be in STEM. We've got to learn the whole thing once. And then when we go back and learn that early material that seemed kind of confusing, we see how important it was. So I'm asking y'all to be patient. It's perfectly normal if or when you fall in love with this stuff to want to go review all of it again. And I would encourage you to read other textbooks on linear algebra. But again, to review, the branches of math and science important to the data sciences, and this is in an all-inclusive list: algebra, linear algebra, trigonometry, statistics, the calculus, and of course, computer science and computing, etc. So how to determine if some V, which is a subset, and I shouldn't call it a vector, I just want it to be V. Some V there we go. Did I just say that on YouTube? Sorry, guys. If some V, which is a subset of the real space of n-dimensional real numbers, is also a valid subspace of all real numbers of n dimensions. So and I need to fix all of these, so it'll be good for you to see what I'm doing here. Just to be consistent, it's still good to wrap a variable name in dollar signs to make it look latexy, latex math. Let me catch up on the chats here a minute. Good, thank you, Hugo. So you're managing the chat. Okay, I'll go fix these later, but they shouldn't have that vector symbol over them. So V is a valid subspace of real numbers in n dimension if the following three statements are true. And this is going to be a fun lecture, by the way, not like last week. If V contains the zero vector for n dimensions, so meaning, now it would be good to stop and do this one. I want to show you what this should have looked like. We really want to say it's a vector of zeros. So that's how we're going to say that. So if this set V contains the zero vector, which means that all vectors in set V are linearly independent of each other, and no vectors in the set V are linear combinations of each other. So that's the independence we were talking about above. And it would dictate that, oh, the only way to get the zero vector is for C1 and C2, et cetera, down to Cn for the number of dimensions we had, or I should say Cm for the number of vectors we have for this subset. None of them are dependent on each other. So again, we're talking about how to find a valid subspace of real numbers of n dimensions. And then, but the second rule is if X is in the set V, some vector X is in the set V, then Cx in other words, any real number C, we multiply that X vector by is also in V, where C is any scalar value. And then the third rule is if A, some vector A is in the set V of vectors, and if B is in the set V, then A plus B is in V. So what we're saying is we get the zero vector, and the rule for multiplication and addition holds. This all means that if the subspace is closed under I should say, funny how I catch more when I'm lecturing. If the set of vectors, let's do this right now though. If the set of vectors V is closed under multiplication and addition and contains the zero vector, it is a valid subspace of the real numbers within dimensions. Okay, now, you may be wondering, so what? You may be wondering, I'm not sure what we're saying. This is a good point to just push the I believe button. This is that thing where you can't understand completely yet why this is important to the plot until we get to solving sets of linear equations and how we do that and why all these things are important mathematically. We're just laying it out right now. In fact, any professor in the world teaching you this would ask you, please just accept this. You'll see why it's important later, just like if you were reading a book. So let's go through some super simple examples. Let's start with the simplest example we can do in three-dimensional real space. So here is a subset. Now, it really is this vector V this time. V equals 0 is a subspace of a real number space in 3 dimensions. Well, we're asking, is this a valid subspace? Well, let's check it by those 3 rules above. Does it contain the 0 vector for 3 dimensions? Well, yeah, because it is the 0 vector. Now, any value of C we multiply on V is still V. So where C is any scalar value. So yeah, it's but the span of this is just a point. And we can never go outside of the span of that point. And if we add V to V, we still get V because it's 0. So this vector V is a valid subspace of 3-dimensional space. Now, even though this is trivially simple, it's still a valid subspace. Okay, another simple example. We've got x1 and x2. So this is any value x1 and x2 for a 2-dimensional vector. And we're saying it's a set in 2-dimensional real space. We're saying but the condition is that x1 is always greater than or equal to 0. So we're going to ask, is S, this set of vectors, is S a valid subspace in 2-dimensional real number space? Well, S does contain the 0 vector for 2 dimensions, but not all C times x1 and x2 are in S. Why? Because if C is all real numbers and we use a negative number, it's not going to be x1 greater than 0 anymore. It's going to be x1 less than 0. So not all C times x1 and x2 are in this set of vectors where C is any scalar value, so S is not closed under multiplication, but any A that's in S and any B that's in S, when added together, are still in S. So it is closed under addition. But what we're saying then is S is not a valid subspace in 2-dimensional real space because it's not closed for multiplication. It violated rule 2. So let's illustrate this with Python. And we did this last a week. We've done it before. So first, we're just going to, by the way, this is just because I'm in dark mode, both in Chrome and in Google Colab. It's just to help me get back my grid lines and tick marks and stuff. So that's all that's for. This is something I'm creating for storage so I can reuse the vector span that I'm about to create. And then I'm just setting the figure size here, so no big deal. And then here's the first thing. This is x1. And x1, remember, it's got to be equal to or greater than 0, according to the way we're describing this set of vectors. And then, but x2 can be negative infinity to positive infinity. Now let's remember, I'm only using integer values, but in reality, I could fill in an infinite number of fractional values between here and here in this plot. In other words, this is a step size of 1, and you don't have to define it that way. I'm just doing it so that it's ultimately clear. But if there's no computer in the world that could actually do this in reality, and even if it could, with infinite computing power, it would take infinity to plot it, and we wouldn't have a screen big enough to look at it, even if we scaled it. So we have to use our imaginations of, we're talking about infinite spans, but where x1 is greater than 0. And so we're just looking at the integer values and using our powerful imaginations that God gave us to go beyond that. So I'm saying on the fly, X is a NumPy array combined of X1 and X2. And I'm going to go ahead and add that NumPy vector to this list. I'm going to append it to this empty list that I created right there. Then this is our trick to get, well, this and these are our tricks to create a space so we can just plot these arrows. Remember, that's our key vector visualization trick, is all that is. And so we're going to plot the arrows of the first component of the vector x, which is x1, and then this is our x2, like we defined in the set above. And then, yep, we get the span, okay? Now we're going to apply those tests programmatically. So first, I'm just looping back through to make sure I can grab all those vectors we created from X list. So this is really just a repeat of above, but again, I appended all those vectors right in here. I'm just reusing them right here. I hope that's clear. All right. Now, let's do the first test. We're really just going to say that now this is a great function when there's some convenient code reason, you need your NumPy vector to be a Python array. And so, or your NumPy array to be a Python array. And there's a reason I wanted to do it. I'll explain it. But all I'm doing here is saying for every vector or array in X list, let's turn it into a Python list, okay? And then I'm just asking, hey, is the 0 vector in this Python list of lists? And it says it is. So awesome. Let's do the next rule. But it's actually the third rule first. We're saying, okay, I'm going to grab some random I'm just going to grab one random NumPy array from X list, and I want because it returns it as a list. It's a list with one value in it. So I'm just taking the first value. That's all this is. And I'm going to take some list too, and these are NumPy arrays. I'm going to sample it too. And I'm just saying, I want to print those. And then I'm going to use NumPy's power of just adding those two. And I want to make sure that if I take this sum of any two lists and make it a Python list, that it's in that Python list of our Python lists. And sure enough, it is. So I random sampled and got 10, 13, and 5, negative 16. And if you look, these are in the set S. And if I add them together, I get 15, negative 3. That sounds like that should be in that set S, so it's true. And by the way, we could have done a different method here. We could have just said, is the first component of each of these vectors positive? And then it wouldn't matter what this value is, and it would still be true. So I can imagine why I'm saying that is if you keep random sampling, this may say false, because it's just going outside the size of the vector set that we saved when we did this. But don't stress over that. So the next thing is it true by multiplication? Well, first, I just replot all those vectors again, our finite span. And then I'm going to create this Boolean empty list. And I'm going to set up, this is the vector I want to see, will this stay in this subset S if I multiply it by any value C? And we already know what's going to happen. If I go from negative 10 to positive 10, by the way, the reason I do +1 is so it will include 10, but it won't include 11 in this range statement. And it's stepping by 1. So let's go ahead and put that there. And again, this is our fake tiny white plot to form this. And then we make sure the limits are the way we want them down here. But again, we're just plotting arrows. First, we plot these C times x0 and x1. Now that's this x this time. And so we're looking at all those scaled values from positive to negative. It would be infinity, but again, we don't want to take the time to wait for that. And then we're calling the current vector C times X mathematically. This is just for plotting here. And so we're going to append to this empty Boolean list the current vector converted to a Python list. We're asking, is that Python version of the current vector in our Py list of Py lists, meaning the original arrays again? And sure enough, we can see visually that it's going out, but we can also see by this test. Well, since you started at negative, all these negative values, of course, are not in there. But once you get to positive, they're in that set. And so this is just a quick mathematical visual test to see that, hey, if we scroll back up here to where we originally asked, in this set of vectors where all x1s have to be greater than or equal to 0 and x2 can be any number in real space, can that be a valid subspace of two-dimensional real numbers? It cannot be, because it doesn't hold for the multiplication rule. It's not closed under multiplication. Okay, so we were here, then we went here, and then we were just here. Now we'll go down to the very next set. Very general example for a span in Rn. Let me make sure that's where we were. Yes. Okay. Now, note that in this example, we don't even know the number of dimensions of n. So this is pure mathematical thinking here. We're not going to visualize this with Python because we're making it so general. So we're saying U is a span, or U is a subspace. It's a span V1, V2, and V3. So we're basically, remember, when we create a span, it's all real numbers multiplied on this vector, and all real numbers multiplied on this vector, and all real numbers multiplied on this vector, and that gives us a span. So we have to use our mathematical imaginations right now. So we're asking, is U equal the span of this, a valid subspace of R in n dimensions? So that means that each of these vectors are n-dimensional, but we don't even know how many dimensions right now. So I got to fix some things I see already. I shouldn't have had this, and I should have a question mark at the end because I was posing a question. Okay. Well, let's check it. If I multiply 0 times V1 and 0 times V2 and 0 times V3, and 0 is part of all the real numbers, then I will get the 0 vector. So, yep, it will yield the 0 vector. Now, is it closed under multiplication and addition? Well, if I define some vector x to be C1 times V1 and C2 times V2 plus C3 times V3, well, that's just, yeah, okay, that should work, but let's just keep checking. If I multiply A on X, that's just A times C1 and A times C2 and A times C3 acting on each of these vectors. So then I can just say, well, AC1 is C4 and AC2 is C5 and AC3 is C6. So all of these are in the span of U, which is our subspace. So U is closed under multiplication. Well, let's define another vector similarly like X, but now we've got Y times some D1 on V1 and D2 on V2 and D3 on V3, where these D's are all part of the real number set. If I add those together, I've still just got a scalar multiple on each of these vectors. And because X plus Y just ends up being a linear combination of these, which would still be in the span of U, so U is closed under addition. Now, if you're confused, just hold on to as much as you can understand right now. But I assure you, if you're confused, you're most likely overcomplicating it, or it's just a lack of familiarity with doing vector math. But don't give up. You will get there. So now let's go down to this. A simple example of a valid subspace in two-dimensional real number space. So is U equals the span 1, 1, a valid subspace of two-dimensional real space? Well, first, we multiply 0 times 1, 1, we get the 0 vector. So this rule is valid. If we multiply any C, oh, yes. So if we take X is some value C times our span, our U, we get CC. And all CC would be in U, because we're talking about the span. Again, the span is, I mean, this really is the span. If we say C's are all real numbers. So U is closed under multiplication. But what if I had some Y now equal to D times our vector? Now I have DD, and that would be in U by the previous rule, but also X plus Y is just two scalar values. So that's just a linear combination of 1, 1, and with us being U, so U is closed under addition. Now, if you're thinking, that seems overly simple, you're getting it. That's exactly right. It's overly simple. So what we've concluded, because it passes these three rules, is that U, which is the span of this 1, 1 vector, is a valid subspace in two-dimensional space. But let's note something. We're in a two-dimensional real number space, and it's only defining one dimension along this line, but it's a subspace of real dimensional or two-dimensional real space. So let's visualize this. Well, here's that span. It's what we've been doing above, nothing new here, except we only have one for loop. Oh, because we're in one dimension. Shift tab. That's what I'm doing right there. So I'm just looking at this to say, okay, as I multiply it from some negative finite span to some positive finite span, yeah, it's just various scalar multiples of 1, 1. Now, what are we doing here? Well, let me remind myself what we're doing there. Okay, just validating that my saving of X list is reusable. That's all I was doing. Too simple. Okay, now I'm just asking, is 0, 0 in my list? Yep. Again, we're just doing this conversion with this list comprehension to use the convenient. There's some things that are more convenient in Python and some that are more convenient in NumPy. So I just switch them back and forth as the mood suits me. There probably is some way in NumPy to check that this 0 vector would be in the list of NumPy arrays. Okay, now I want to see, well, if I random sample any 2 vectors from X list, will they add up? Yep, they're in that list. Any 2 that I can add up. Again, I'm cheating because I did the addition before the multiplication. And then I said, okay, I'm going to create this Boolean list, and I'm going to see, is my current vector defined by this inside my list of vectors? And sure enough, it's always true. Now, of course, you could make this false if you're not careful to stay within the bounds of the vectors we saved. But we're just, I hope y'all are feeling like, wow, this is really simple. When do we get to the cool stuff? And it would be like saying you want to get to the cool stuff, but it's on the other side of the Grand Canyon, and you can't just jump across it. You got to climb down and walk through it. That's what we're doing. But we're going to get to the beautiful other side of the Grand Canyon. So now we get to something cool and new. The basis for a subspace is a set of linearly independent vectors. In truth, it's the minimal set of vectors, the perfect set of vectors you need to find the basis for a subspace. So let's look at this mathematically and then visualize it with Python. Let's say that V equals the span of these vectors, V1 through V sub m. And we're saying that's a subspace of R to N. We're already saying we did all the checks above, and it's a valid subspace of n-dimensional real number space. And, oh, so I cut and paste, sometimes I forget to get rid of these residual parentheses. So where each of the vectors, V1 through V sub m, are linearly independent. That means by definition, no vectors in V are linear combinations of other vectors in V. Let's put that another way. If I take the unit vectors of all these, I won't find any 2 unit vectors equal to each other. Or if I scale them all different ways, trying to find 2 vectors that looked exactly equal, I wouldn't find them. That's what we're saying by this independence. Now, if S really does equal this, S, oh, funny, didn't it? I don't know about y'all, but I think it's really worthwhile. I hope y'all feel the same. You don't have to do this stuff in LaTeX. You could do it a different way. I just think it's a great practice to learn it and use it, and it makes the presentation so much nicer. Okay, now let's say, so S equals this is a basis for V, meaning it's the minimal set of vectors we need to really define that subspace. Now, let's say that we had some other set of vectors, V1 through Vm, but also had Vs in this set. But Vs in actuality equals V1 plus V2. Well, we could say that the span of T equals V is still a valid span. It's even still a valid subspace, but T is linearly dependent, and thus T cannot be a basis for the subspace V. Why? Because Vs added some redundancy. We could find a linear combination of two other vectors in this original set that equal Vs. So it doesn't form a basis because it's given information that's not helping us define this subspace. Again, it can still be in a span. It can define a span, but even for that span, it's defining information that's not needed. Let me just get a drink here. No, are there any questions? And by the way, guys, everything's fine. Saying, Thom, I kind of understand this, but I don't know why it's important yet. That would be fair. When we start really getting into the power of linear algebra, and we see problems when we're trying to solve these giant sets of linear equations that relate to one another, all of this, you'll go, I'm so glad you beat that to death, Thom. And I can see why Saul starts out with that stuff now too. You'll really appreciate it. But I can imagine right now it's kind of like the compulsory stuff you have to do before you get to the cool stuff. However, getting good at the LaTeX and then growing your Python skills is definitely a great benefit. So an example of basis of a subspace. We've got the set of vectors 2, 3, and 7, 0. And this S is the, this set of vectors is the span of S a basis for two-dimensional real space? Yes. Let's show why. So first, please note that S is not the only basis for two-dimensional real numbers. Now, I want you to see Saul's lecture for how to prove all of that, prove this statement algebraically. But note too that the two vectors are independent. I mean, if what would be the unit vector of this? It would be 1, 0. And what would be the unit vector of this? Well, it would be 4 plus 9, that's 13, square root of 13. So it'd be 2 over the square root of 13 and 3 over the square root of 13. Those two unit vectors are not equal. So we see the independence right there. In other words, no matter what you do, one of them cannot be defined by terms of the other by scaling one to match the other. And turning them into unit vectors is a valid form of scaling. So let's apply the rules we covered above, but we're going to illustrate below with the code that we reused above. Okay, we've got a question. Yes, Hugo. You're on mute, buddy.
Okay, today's my day, so I get to
wait. Let me show people what we do when we know someone's talking on mute. Thom, your hair looks so amazing today. Oh, thank you, Hugo. Okay, what were you going to really say?
So I was going to ask, that scalar, usually a scalar is just one number, right? It's just
Yes.
a
Well,
single number.
right. Yes, exactly.
Okay,
But
so would it be right to say you can
any
scale
real number.
yeah, any real number? So would it be right to say you can scale a vector by another vector, or it has to be a scalar?
When we say scaling, it is a scalar.
Okay.
And they're not
So
spelled the same way, by the way. Scale, they're related, of course, but.
okay. So now, why do we want to scale a vector, for example, this 2, 3, and the 7, 0 vector? Why would we want to scale them? Is there a particular reason why we scale one vector to try to either, is there a particular reason? I've
That's
been
a
trying to
great
grab
question.
that, yeah.
Yeah, no, that your question is going to help everyone. So remember, we're looking at stupid, simple things. But in reality, a lot of times the math is too many numbers to see really easily. The reason, one of the motivations to scale is to see if we can get any two vectors equal to each other in our set of vectors. That would mean they're dependent on one another. And that would mean that we have more vectors than we need to define things for us. So that's one reason we do it, but there's a lot of other reasons we scale. But for right now, that's the reason we care. That's why we looked at, in other words, coming up with the unit vector is a way to scale a vector. And the reason the reason we've done it here, and we're going to show it again, is to say, hey, I want to check if this set of vectors, if all these vectors are independent of one another. I want to check to see, are there any two of them that I could add together that would equal another vector in the set? That's what we're looking for, because we're looking for the minimal set of vectors that will define a subspace for us. Does that help, Hugo?
It does, but I'm trying to marry it, because one of my favorite ways of solving systems of equations many years ago, almost 20 years ago, while I was taking my linear algebra classes in secondary school and in the university, was by using matrix algebra. So whenever I had a system of equations, I just, like 3 equations, 4 equations, I just crank up matrix algebra and then solve. So, but now, because I'm very rusty when it comes to linear algebra, I'm just trying to remember everything. I'm just trying to understand now.
We are working back toward what you used to do, but we're laying a really strong foundation to understand what you used to do better, and then we're going to use Python and NumPy and even SciPy to solve this stuff. But when we solve it, we're going to know what those libraries, what math, what coding those libraries are going to use. In fact, Hugo, remind me, when we finally get to where we're using the linear algebra module and the SciPy tools, let's go look at the source code together. Okay. It's actually easy to look up and find. So first, I'm just going to do the span of these. Now, finite span again. Remember, we call it finite span, and I'm just doing the span of those two vectors, and this is what it looks like if we do it in integer steps. Okay, and so let me say, let's illustrate below with some code reused, modified from above. But remember, we have to imagine the space with the CIs of all real numbers. We're only using a finite set of the CIs. Now, I was expecting to see more, but I think we can see right away through what I already described. And yeah, I'm asking you to relook at Sol's algebra if you don't already get it. but these are clearly independent of one another. But we could also use all those checks above. In other words, the check where we said, let's turn these into unit vectors and make sure they're not equal to each other. So that's one way to make sure they're independent. So what I'm saying is these two vectors are a set that they provide a basis to define every point in two-dimensional real space. That's all we're showing here. So we can see that if we increase the limits of finite span, we could keep making this plot bigger and bigger. Okay, now, what is another example of a basis of a subspace in R2? In fact, let me show you all what to do here. And it might be fun at this point, since we're getting near the end. I'm going to show you all something I chanced upon. I start a $sign, I start a backspace, I wait a second. Ah, shoot. Somehow I happen on, you can just type any letter and get this list, and it'll stay there for you. And you can see that's how I get that real. But I can get all these other symbols. In fact, I can go up higher. There's all these readily available things. Now, once you use one of these, though, the trick is it turns it into that character right there. You sometimes need to just do it this way, but some of the things it suggests you can just type out too. So I wanted to show you all that's how we finally got that fancy R that defines all real numbers. Okay, and this is the nice way to put big brackets around something. This, if I show you here, we go here. We want the environments. These are, you'll use these a lot in this class. So here's the code to get the curly brackets around something, but you could put this code inside this code right here, and that's all I have done. So when you guys are trying to do it yourselves, that's what I just said, the little b and the big B. So the big B is for the curly brackets, the little b is for the square brackets, and that's why it looks like this. And I have the two vertical vectors here. So we're saying t equals these two vectors. We're saying, is the span of this t a basis for two-dimensional real space? Yes, it is. I needed to say it. I don't know where my period went. Oh, there we go. Okay, now apply the rules that we covered above and see Saul's lecture for how to prove it algebraically, but let's just illustrate again below with some code reused and modified from above. So this is the same stuff we've been doing. We can see as if I keep increasing this finite span, this is going to cover everything in two-dimensional real space. And again, we're stepping by ones, but if we went to infinitesimal values, that means tinier and tinier values, this would just be solid green, right? So, guys, that's it. If your two vectors are truly independent of each other, I can't scale this one to make it equal that one. Or if I had a bigger set with larger dimensions, I can't do a linear combination of the two to make them equal to another vector. Then all of these are independent and they form a basis for a subspace. Now, what's another basis? Let's see, hang on. Counterclockwise, 2D vector by be achieved via adopt. Yes. No, we're not seeing that yet. We are not seeing that yet, but we will. In fact, we're coming up on those lectures from Saul here soon. But let me show you one that's so simple. Let's cheat and copy all of this. And let's go create a new text block right here. And I'm about to take questions. I just want to show you all this real quick. Let's just exploit this even further. So I'm just going to make 3 dimensions now, right? Copy and paste is the best cheat in the world. Now we can, I hope you guys agree that we can readily see, almost, it's just too simple. This is still about another example of a basis of a subspace for all 3-dimensional real numbers, or all numbers in 3 dimensions, all real numbers in 3 dimensions. I'm not sure the best way to say that. We're applying the rules that we covered above, but basically these are a minimal basis. Now, what's an example of a vector that we could add that would make this not a basis? So let's modify this yet a little bit more. We're going to put in a 4th vector. And I hope this just makes it super crystal clear. And then if you guys keep coming back to this, I think you're gonna just, okay, now you see I want to force more space. Let's do that together. Not yet, but if I put another one, again, this is markdown, so you can force it into HTML mode, basically. Oh, darn, then did more than I wanted because I added that space. Okay, we're going to add yet another vector, and we're going to call this one U. And is the span of U a basis for R3? No. And why? Well, first of all, I haven't finished defining this last one. Okay, now this is kind of fun. Help me with this. Why is this not a valid basis for all real numbers in 3 dimensions?
Because the sum of the first 3 is equal to the last vector.
Kelvin, you're a genius. That's exactly right. And I think you described it better than I could have. It's because the sum of the first 3 vectors equals the 4th vector. Exactly. And just to be more fancy, let's do this. It'll just look more latexy, but I'll show you why. And if you haven't learned this trick yet, when you want more than one character to be in a sub or superscript, I'm going to do superscript here, you just put it in curly brackets. There we go. That's exactly right. This is not giving us any new information. What we want is something that's non-repetitive, that tells us everything we need to know with the minimal amount of information. Is that clear to everyone? I mean, I was such a brat when I was first learning algebra because I was already good at math, but my teacher was so wonderful. And I would just think, why are we doing this? I can just see the answer. And Thom, you need to learn the steps for harder problems. Being such a brat. So that's exactly right, Kelvin. Let's make this look a little better too. All right. Now, any questions? And those, the code above that we use to test for valid subspaces, that could still be applied, but I think that code can be improved. So if y'all want to do that for a group homework assignment, when y'all get together to do work together, I think that'd be great. Okay, what is going to be next? I mean, this stuff was important, but now we get into some really fun stuff. And the visualization tools we can use for it are fun too. So we're going to start getting into dot products and cross products of vectors. And just watch as many of these as you can. If you don't get through all of them, comfort yourself with the fact that I don't yet know how many of our Python lectures it will take to cover these, but you really do want to do your best to understand these before we come together, okay? And then, let's see, go ahead and give the link here again, just so y'all can get back to Saul's lectures quickly. So they're in the chat. And yeah, I want to take questions or just let's talk about this. Yeah, Hugo's given the location for this this notebook. Notice that I have it anyone on the internet with this link can view it. So that's so that nobody can mess it up. But you can make a copy of it and make changes to it for yourself. And I strongly encourage everyone to do that. But are there any questions at this point? Is there any point in this notebook y'all would want me to scroll back to right now?
Personally, I think this class went very, very well, and it was far better than what we had last week.
Yeah, please delete last week's lecture, Hugo. Please.
I'll do that.
I mean, for my own reputation, even, right?
I'll do just that. I'll do that right.
I got to tell y'all something. Before I had my PhD, but I was a lecturer at a university, and it was going well. My students liked me. I was enjoying teaching the class. But I kid you not, there was one day I had prepared. I went up to the board. I was starting to explain things. I realized I had made some mistakes in my preparation. And I looked out at my students. I said, I'm really disgusted with myself right now. I want y'all to take a walk. When you come back to the next lecture, I promise I will make up for this. And I did. But, you know, it's okay to say, oh, I screwed up. Dr. Ives screwed up. So just want y'all to know, you're not the only ones that struggle with this stuff. Let's all always remind each other, this is beautiful, powerful, conceptual stuff that applies to reality, but it took our brilliant predecessors thousands of years to develop this, and we're still, you know, finding better ways to exploit it to the good of humanity. It can be hard sometimes, but yeah, last week was really more like, do not try to lecture and do LaTeX at the same time. That is not a good practice. Whereas I'm familiar enough with Python to where I can code and talk in that at the same time. So what we're going to do is I will have as much of the LaTeX prepared ahead of time, but in the future, I won't just present the code like I've done. Now, the code that we use today is no big deal because we've been over this code before. And again, if there's a piece of code you don't understand, break it down and play with it, okay? That's what you really need to do. For example, you're like, oh, what is Thom doing there? We'll just do this. Print V1, and then print V2. I mean, just break it down to smaller pieces and really seek to understand it. And then, you know, just take it a step at a time. Well, okay, use this finite span. Oh, he's using like Control Shift L. That will highlight all the other ones. Oh, that's what he's doing. You know, I don't like that name. I'm going to do, just call it 5-SPA. You know, see what I'm doing? Multi-cursor here. You can do all of that you want. Okay, so you come in here and make these your own. What's another thing? This lim is so that I can change these values at will. So you look at all the instances of that. That's so that I don't, if I need to change from 30 to 40 for some reason, I can change it in one spot. That's why I do stuff like that. If you're not clear on this and why we do this, all you need to do is go up to the very beginning where we learned how to do all this. And looks like I need to put some subheadings, but we were just learning, frankly, to plot vectors. And that's all we were doing in the beginning. And that's why we did these. We learned later that we didn't need to do this. We used those limits. So in your versions of this book, you could go notebook, you could go fix that. Down here, for example, we could fix that stuff above if you're also in dark mode, that is. I'm doing a control copy. I'm going up here. I should have gone here. And then I basically just say, oh, you know what, I'm going to need that here if I want to see those axes, so I can rerun this, and boom, I get those things back. And now that will be defined for the rest of the notebook. But it might be good. I try to keep these cells so they run independent of one another if you just come in and see them. So if you're also loving dark mode in both Chrome and Colab, you could copy that statement in multiple places. You could fix this so we're only printing the one, doing the one plot and then having the X limits. We didn't do that at the very beginning. So just make these notebooks your own, but when you don't understand something, you can always just send me a message in our Slack. It's best if you do it in tech chat so others can see the question too. But if you feel like a little shy about it, it's fine to send me a direct message in Slack or on LinkedIn. Okay. Any questions? And or anything to add? And you are on mute. So
I just had a general question. So is this knowledge that we are acquiring right now, is it like the foundation to the machine learning? Is the machine learning the final destination of these classes?
Yes.
Okay.
Absolutely. In fact, what you'll see, Kelvin, is because you're going to understand this stuff so deeply, it's going to be really clear to you how to code linear regression from scratch with ordinary least squares. Even it's possible to do it without ordinary least squares. Do it the way Hugo was describing, but we're going to code that. In other words, you're going to learn how to find the inverse of a matrix. You're going to learn by coding from scratch without NumPy. Using these principles, you're going to learn how to solve a system of linear equations. When we have more equations than we need, you're going to learn how to use ordinary least squares. You're going to learn how to use generalization techniques, and all of that's going to make super clear sense to you because we went through all of this. So you said it perfectly. In fact, Kelvin, when you're ready to lecture for these, you let me know. I think I'm going to let you take over. You say things very clearly.
Yeah. Thank you very much. This was a great lecture. This is my second one, but it has been great. Yeah, thank you.
Excellent. Oh, you're very welcome. Let's go ahead and clean this up too. Here we go. You just have to make sure that statement's been run once, really. But once it has been, we get those axes and their tick labels back. Okay, Hugo, I'm getting the sense that I don't see anything in the chat. We've covered everything in good time. We could give everyone a break before we do mentoring time. What do you think?
Absolutely. It's great. It's great.
I feel so much better after this week than last week, but it's because of last week.
I've removed the video. I've removed the video.
Thank you. I think I feel so much better because I spent good preparation time last night, felt good about it, and then, you know, if it worked for last week, I wouldn't feel so wonderful this week, I think. Hey, you bet. Iodeji. Oh, good. I'm glad. Thank you. You know, this probably won't be last week probably won't be my last fiasco, but we will always try to minimize them together.
Right. Right.
Okay. Now, again, make copies of these Google Colab notebooks and play with them and change them up if you want. Make them yours is what I'm saying. We all plagiarize each other's code, so never feel bad about that. But if you try to give me credit, it helps me reach more people to help more people. But also it makes you look good that you're passing on credit from someone else. Like I'm always praising Kuya Tran because who doesn't learn a lot from her, right? And I appreciate when people like what I'm teaching on LinkedIn and in these things. Let's just keep learning more together. That's what we need to do. And if you can't ask and answer questions as brilliantly as Kelvin, please don't be shy. Come off mute and say, I'm not sure how to pose this question, Thom, and I'm going to tell you right away. I know I've been there too, so don't be shy. I mean, I wasn't always this knowledgeable, and I still have a lot more to learn in my mind. So I just want y'all to be very comfortable to ask questions, and you can give private feedback through Hugo too. All right. Let's see.
Okay,
Someone was about to say something. Okay, good.
Yeah,
I'll stop
good.
sharing now. And all right. Any last questions before we go? All right. I hope y'all are finding this valuable. If you're enjoying it, invite some friends to come with you. This is totally free. There's no people can come, but this is learning machine learning the hard way. It's like
I think that should be the title of your next book, just like Zed's book, Learn Python 3D Hard Way.
yeah, exactly. I love those the hard way books because
Yeah.
you know, going through the linear algebra and then see Kelvin, what you were asking. Now we'll learn linear regression, but what more do we? In other words, this linear algebra is the foundation of linear regression, logistic regression. But what else do we need? We need a little bit of calculus. We don't need all of it, but if we keep going this way with this foundations method, and Hugo and I want to, we will get to where I can show y'all how to do calculus without knowing calculus, because the symbolic solvers are there, but we want to make sure you at least understand the principles. Now, did I study analytical calculus and differential equations and multivariable calculus? Yeah, I did. I just studied math beyond that. Does that mean when I have a hairy equation, I always know how to take the derivative of it? No. And in fact, even if I think I know how to get the derivative equation, for a function, I still go and use one of the symbolic math solvers. And guess how much the one I use costs? $0. It costs $0 and it works great. So let's say we've moved through linear regression and logistic regression, and now we're staring at neural networks and how to derive them from scratch, both mathematically and how to code them from scratch. If we keep going together, you guys will know how to do that, and we'll use those symbolic solvers to take differential take derivatives of functions that we need to take derivatives of, to know how to derive the back propagation for a neural network, which will take us into deep learning and various types of there's a myriad of different neural networks that do incredibly amazing things. We can even get into transformers together if we keep going, but it will take time, and it will be, but you'll know it at the very depths, like someone that would know how to code it from scratch. So hope that gets y'all excited, but it'll take time.
It is exciting. What we can try to do is see how much of it we can compress into maybe, like, let's see if we can finish that within a calendar year. I know you always tell us it's not a sprint, it's a marathon, but I'm really hoping we can, because I started doing my linear algebra classes again, watching Saul's video. One of the things I discovered was that I now had to go back to my geometry, because there were some times I want to calculate, I have to use Pythagoras or some other form of geometrical equation. And then I found myself going back to sines and cosines and, and tangents. Then as I continued trying to work my way through the maze that this whole thing is, I discovered that when you have a system of equations, like you create features, from machine learning algebra, then the next thing that happens is you want to find the global minimum. And to get the global minima, only differentiation can do that. So we'll have to venture now into differential calculus. And then from there, we'll keep going. And so I now see the linkages of all kinds of mathematics coming together, because by the time we get there, we'll start talking about normalization. Then we'll start talking about all the statistical tools that we use, or would I say math that is borrowed by statistics, or stuff like that. So I started now seeing the linkages, and I really am grateful. And that was when I made up my mind, you know what, I think I'm in this for the long haul. So I know it's not going to be like something we can finish in, say, 6 months, especially since we're doing it every Saturday. But I just know we'll just keep doing it. We'll keep getting better, keep taking real life case exercises and coding this stuff up, and then we'll be fine. I just know that that's why I'm excited.
Yeah, exactly. And I want to encourage y'all, don't do this unless you can afford to, okay? But I give to Khan Academy. It's amazing how much you can learn there. Really, I consider Saul Khan one of our partners in what we're doing here. He doesn't, I don't think he knows we're doing this, but he doesn't have to. I still appreciate him. And we're going to leverage from his great lectures. We're using that to help us develop our Python skills for both visualization and understanding. And what you'll see is that we will use NumPy and SciPy and TensorFlow and PyTorch. We're going to use those, but you're also going to know, you're going to feel like I could join the coding team that coded that stuff. Yes, you could. You may not be able to do the GPU level coding that does the parallel computing and, incorporates that. That's heavy duty coding stuff. But as far as just knowing how to code it to do the math part, the non-computer science part, the math part, you guys are going to feel like heavy duty guys, very much so. So, all right, I could ramble on and on. So want to keep this as short as possible. And then, but start watching. You're going to start to have fun. We're going to introduce a new tool, Visual Python. And that's so we can dynamically see some fun things with these cross products and dot products. So I hope you'll, if you can find an intro to it, that'd be great. I think you'll have a blast with that too. And maybe we might just have a class where we just introduce Visual Python. So you don't, it's not especially hard, but it's a little bit different animal. You know how you start learning pandas, and it's Python, but it feels a little different. NumPy feels the same way. Visual Python can be like that too. All right.
All right. Okay. Thank you.
See you guys.
All right. Thank you. Bye, everyone.